So my name is, let me turn this on. Yeah. So my name is David Duncan. I'm a Partner Solutions Architect for Amazon Web Services. And Kevin Ayers helped me to develop this slide deck, and he's not here today to speak with me, but he's here in spirit, and we're
If anything goes wrong,
yeah,
it's his fault.
that's right. If anything goes wrong, it's his fault.
These sessions will be posted.
That's right. So what I want to talk to you today about is I want to give. I'm hoping you're going to leave the room with more questions than you have answers. There aren't a whole lot of big discussions around building AWS or building HPC solutions on top of AWS. And I've had a lot of conversations that I feel like Spark need to have more conversations, and I'm hoping that this is going to continue to do so with a wider audience. So obviously all of you know that lots of customers have lots of pain points around building out their own HPC solutions, and so there are a wide range of things that are identified, but within the SUSE community there are some that have been talked about, discussed, and highlighted previously, and those are kind of the usual suspects, just managing the complexity. Nobody wants to have the day-to-day job of ensuring that images are the same, or you have a different kind, that you have everything set up for whatever specific workload, your batch scheduling is functioning like it's supposed to, your priorities look like they should for your management, etc. And then maintenance, the same thing. Nobody wants to put diesel in the generator to make sure that it still kicks on when you're trying to complete that mission-critical job. And then, of course, it's always best to complete faster and on time. And from an economics perspective, there is forecasting that says that we are going to see this continue to advance even into 2020 for a much larger part of the market share, up to more than $1.2 billion increase through 2020. There are lots of projects that have been done on SUSE, and while a lot of these projects are done on premises and configured and built on stacks that are specifically leveraging technologies that are on premises, there are many, many models where customers would like to do test and development in an arena that is free of the restrictions that you have from your priority-based scheduling, right? So you want to get right to what you're doing. Currently today, and one of the reasons that this slide is part of the deck is that this is an ARM HPC ecosystem, and something that I want to call attention to here. This SUSE has had a long-standing technical enablement on ARM, as well as HPC. This is a fairly large system. The Leibniz supercomputing system is one that I think identifies a fairly broad range of calculations that and configuration management that is specifically going to have some overlap with what I talk about immediately after this in the AWS space. And then NVIDIA obviously is a fairly large part of any kind of GPU processing that customers are doing today. There is full support for NVIDIA on SUSE at this point, and it is getting even better in the future from what I understand as Robert Speichert's team over here at Public Cloud team continues to advance their participation in the building and support of the NVIDIA drivers now for graphics, but potentially.
Well, so the CUDA framework is available for SLES 15 and for SLES 12 SP4. and our HPC team, like we're just a product manager.
Project manager.
Project manager.
James.
James. They're continuing to work with NVIDIA to make sure that we continue to support every service pack along the way.
Univa has a grid engine, and with respect to SUSE, they have come together to create a management interface for the Tsubame cluster, and that cluster itself is touted as one of the most open in the world, from what I understand, right? So availability on this cluster this cluster is available for anyone to use, which makes it a very good fit for the open source operating system. And then another fully supported configuration with SUSE is Bright Computing's management system, and their management engine provides a lot of support for a great number of clusters, doing a vast array of jobs and working at a scale. So, why do it in the cloud? It turns out that customers continue to have the same kinds of issues that they do on premises. They're out of architecture, they want, or out of infrastructure, they want to increase the amount of space they have or the number of compute nodes that they have that are available to them. They want to find better ways of pricing. They want to create a better collaborative model. So functioning, we have a long history at AWS of infrastructure as code, and so this makes a strong collaboration model for customers who want to leverage the cloud as a component of their infrastructure. There are several cost advantages. Typically when you stand up a large cluster, and clusters are very large today. I remember when 4,000 nodes was a large cluster, and now we're just not even close to that. The huge capital expense up front can be prohibitive for small groups, or even especially small university groups. And so they have to look for some way to do a pay-as-you-go model, or something that matches the grants that they've located. And this is a great way to very quickly find a structure that meets your requirements, but also meets your budget. So, in the world of HPC, it's very easy to get caught up in a single system and to move towards a strategic initiative that provides you with a very good solution to a single strategy. And at Amazon, we try to help customers create a solution that gives them the opportunity to be agile about the direction in which they go, or they deliver results. So if you're looking for a solution, I urge you always to look for a way to not just move forward, but also to move forward in a way that preserves what you have before, right? So this structure, this model is a very critical one, and something that I think is a part of the structure and the infrastructure. So here's some of the popular workloads. Things that we see a lot, obviously Monte Carlo simulations. Genomics processing has become a very big part of the HPC world on AWS, and then obviously transcoding and coding. We have some famous companies that are doing some work there. Companies like Netflix, you may have heard of. A lot of public sector customers, and just general heavy computational workloads. These workloads are being run all over the world. They are run in all 20 of our current regions and across 61 availability zones within those regions. I wanted to make sure that everyone understands a little bit more about how those regions work. So I've added a slide here to just go over a little bit the way that it's a little overwhelming, but just so you can understand that in each one of the availability zones, we have a commitment to low latency communications between independent buildings, independent locations, and then within those we have even lower latency communications between racks or data centers, and each one of those is connected together to create a redundant environment in which the computing takes place. One of the things that you may have noticed from one of the previous slides was that one of the things that is a goal here is to provide unlimited infrastructure. And this is part of the way that we do that is to ensure that we have multiple availability zones that are providing customers with what they need or the resources that they need across multiple zones across a specific region. So within, for example, Dublin there on the other side, there are a minimum of 3 regions that are available to any customer at any time, and those provide redundancy that allows them to manage fairly large workloads. Inside of our infrastructure today, the things that are very much the enablers for HPC within AWS are the compute performance that we have, and we'll go over some of the details of some specific instances that I think are targets for HPC workloads, but specifically ones that are compute intensive, the ones that have GPUs, and then the other ones, the FPGA enabled instances. Instances that have high RAM, high memory, also are very beneficial for some workloads. We have instances that are targeted towards compute intensive and memory intensive to combine where there are combined requirements. Network performance, we really focus on latency. Latency is a very important part of how we define whether or not an availability zone is functioning as we expect. So we try to keep it under about 7 milliseconds latency in between the availability zones within a region. Storage performance, obviously we have a large number of options for storage that are beneficial for HPC workloads. HPC workloads are going to be targeting a couple of different types of storage, right? And one of the things that is very important is being able to support a fairly large distributed storage workload, and there are ways to do that. More on that in a later slide. Visualization is one. Automation, obviously, everything has to be automated. I mean, since the dawn of Beowulf, there's been a requirement that we have automation in place so that if you're running things on the secretary's desk when she's out of the office, you got to be pretty automated. But the remote graphics for interactive applications is one I think that commonly gets overlooked, that we actually have the ability to do more visualization than you might think, right? And there are some tools for doing that, including some that were part of NICE when we were brought over. So here is just sort of an example of where these use cases lie and which of those requirements we think are are required for each one of them. So some of them are more distributed, some of them are more tightly coupled. Some are less data intensive, more computationally intensive, and some are very data heavy, like the transcoding or something of that nature. GIS rendering. So we break it down into, we try to classify into these, sort of three buckets. Whether it's a tightly coupled workload, or loosely coupled, just pleasingly parallel or embarrassingly parallel, or if it is sort of a deep combination of the two, where you have sort of a tightly coupled workload, but in the context of a grid engine, where you can spread that workload across multiple regions. So now we'll go back and look at some of the places where this is very beneficial. Obviously, grid computing examples in this case. The LHC, obviously they have a very large OpenStack cluster as well, but then they take advantage of opportunistic computing and versatile workloads through what we call spot instances. And spot instances are a way that you can, we'll more on that later, it's a way to manage your cost over your instances and take advantage of off-peak times when instances are not in high demand. So there's a little chart over here. I'll go over this more, but this is kind of two charts. One classifying what jobs are running, and the other one identifying how many cores are actually being consumed at that time. And here you can see it a little bit more. So as the number of jobs increases, you'll see that the number of cores that are being used is increasing. And this is being used across multiple availability zones. And they're leveraging that opportunistic compute so that they can decrease their costs considerably. And costs can be decreased up to about 90% this way. So our biggest analytics job so far has been more than 1.1 million VCPUs. So the virtual CPUs here are being used concurrently in this analytics job, and then you can see the provisioning model here follows a little bit of a sort of a cloud-based model, but there's a lot of obviously a lot of growth in the industry for handling things this way. And this started off as a fairly small job, and then scaled out to increase to more than 1.1 million VCPUs. And this is the workflow here, supported by an ingestion through S3 to a DynamoDB, and then through that to the cluster. And obviously the scheduler here is Slurm, which I want to make sure that we point out that Slurm is a great partner of AWS, but also I think an integral part of the HPC module. So that's part of what I think is really great here. We're looking at an example and seeing that synergy come back. This is one of my favorite examples. So one of our HPC leads, David Pellerin, has talked about this specific case and how he was working with the HDST, and one of their scientists was doing some analysis on specific drive changes, and just got enough information to get started on AWS, and he laughs and calls it shadow IT. But once this scientist was up and running, he was able to make some minor changes in his simulations, run those simulations more than 1,000 times, right? I think the actual number he said was close to 10,000 times. More than he was trying to schedule those on his own on-premise cluster. So by bursting to the cloud, essentially, creating his own workload, dropping that in, he was able to iterate on the simulations thousands of times in the time that it would have taken him to do one. And this is a very common workload for us. So let's look at, let's get more tightly coupled, move out from the grid. This is a place where I think people don't start to think that copper might not fit the bill, but it keeps working. So if you look here in our graph, we're looking at, in this benchmark, the C4 8X large, and we're watching as the time to completion decreases as the number of instances increases, the number of cores increases for use here. Structural simulations. This is another one that's where we can look at the same thing. We can look at the decrease in the time to completion of the job as you increase the number of cores that are associated. And this is just scaling up the back end, right, on the C48XL. I made sure to put this one in here for you, Robert.
Oh, that's pretty cool.
Yeah. So here we've got a fluid dynamics example, and you can see over here the number, the decrease in the amount of time to completion of the job, slightly different kind of graph, but versus the number of cores and the number of instances that are a part of that. And historically, I think there's been some concern over whether or not these are supported, so I want to make sure that I like that. So here's another one. This one you can see is leveraging some of the power of the FPGA, right? So we're up over 200 million cell models on more than 512 cores, and the throughput of the job is 600 times speed up over the on-premises configuration that they were using to do the same work. So now looking at some work that can be that can be sped up, so to speak, through the use of massively parallel computing. We see that the massive parallelism we have from the GPUs and the FPGAs can be taken advantage of. So what's under the covers? The P2 and the P3 instances. The P3 is our latest generation for GPU instances, and that is leveraging the Tesla V100. The Xilinx is fully functional with SLES workloads, so you can actually use. So we have a development environment, and the development environment is available through the AWS marketplace. You can build your module, and then you build what they call an FMI which is an FPGA machine image, so that you can leverage that on the FPGA instances. These are, I think I have another slide that tells you this, but there's more than 2 million PLCs available for one of the 8X large instances. So just really quickly, we wanted to look at storage. So a lot of people ask the big question, which is, how do I get my data there? I'll start with two things. One of my favorite projects at Amazon is the Open Data Project. So there are a fair number of data sets that are out there that if you're trying to tune or review or looking at some sort of a specific data that's available through the open data set, that's a great way to take advantage of data that's already been ingested, and there you can create that through snapshots of that data for your own use. But if you need to get it to through your own corporate data center, data transfer methods can be direct. They can be just a VPN connection. They can be through a a software vendor, you can leverage Snowball to, or something like that. We have just a standard export or import model that you can use, just a basic drive, and bring a few terabytes over through your own SCSI device, or you can order one and we'll drive a truck to your house and you can just hook that up to your PCI bus. Getting it out or leveraging some of the tools that we have for data ingestion and analysis, like Kinesis Firehose is a great way to do this if you have a consistent communication model. And then we have new techniques like the transfer acceleration and the storage gateway. Storage gateway allows you to have a storage device on premises that replicates to AWS either in Glacier or in S3 or to EBS volumes. Once you get it there, you can ingest directly from S3, or you can push that to an EBS volume, or you can push it directly to an EBS volume from your import. You can use the localized store for ready access. So if you want to have high IOPS, high throughput for your storage device, you can leverage the local storage on an instance by ingesting that data from somewhere like S3 with minimal to minimize your costs, and then have it readily available to the instance with high IOPS with no additional cost, so you don't have to provision EBS volumes with the high IOPS that you expect. And then we have a couple of other options there. There's EFS, or the Elastic File System. So that's an NFS share that's available, and we have some tools that are packaged in SUSE today that are the EFS utils, which provide some parallelized communications and also a secure tunnel through, I think they used Stunner to do that.
The package is on the way.
Okay.
In the process. We actually made some contributions upstream for security hardening and other things,
Which was great to see. But the EFS utils themselves are not really as, I wouldn't use them as the ingestion model for data. I don't think it's really fast enough today to be the place that point of contact. But a relatively new service that we're offering is the FSX for Lustre. FSX for Lustre is Lustre, the distributed file system, and I have a sort of quick slide just on that. It provides you the division between your data lines and your metadata lines, and the service itself gives you endpoints that you just attach to the instances that are ingesting the data. So if you have a cluster and you need to have attachment at all the nodes, this is a great way to do that. And this is done in sort of the traditional appliance mode for Lustre.
Yeah, I mean, especially HPC applications, many expect to have a file store, so they don't deal well with an S3 bucket, so they want a file storage, and Amazon is the only service provider that provides a file system as a service, so you don't have to run your own instance and attach volumes, so you can just use the service.
So now we'll just go over. I'll start by just giving you sort of a general look at the solution components here, but I'm going to tie this right back down through the center column in compute. So some of the tools that we're using for orchestration are AWS batch service. So the batch service allows you to orchestrate through step functions. So you can identify what should happen after this step, and then make that process hardened and reusable. AWS Parallel Cluster is a tool, and we'll talk more about that, through which you can create a configuration for your cluster and then stand it up and have a ready-made configuration including identifying your scheduler, your storage models, and a few other things. So down through here, you have the storage options that we just talked about. The compute, EC2 spot, our opportunistic compute, has a really important place in our cluster definition, and then also the AWS autoscaling. Autoscaling is a very critical component in determining whether or not you have the right sizing for your application needs. For visualization, we have some tools that are available here, Amazon AppStream and DCV from NICE. And then on the networking side, enhanced networking, that's already in place through the ENA driver. Placement groups is a way of identifying that you want to have instances that are stood up in very near proximity so that you have a low latency communications in between them. There's also something that's called a dedicated host. A dedicated host ensures that you have a single host for a specific number of an instance type so that you can run at less speed. But those are rarely as necessary for HPC workloads. The Elastic Fabric Adaptor is something we'll talk a little bit more about. So when you're looking at what you want to what you want to choose in terms of your processor workload, we have basically we have a fairly large selection of processors and architectures. So we have obviously our very large Intel shop and have many Lake processors, but right now standardized on the Skylake. The AMD, so where we have instance types now that are something like the MD5, if you looked at the family there, and the generation, you'd also see the option for an MD5A, and those are running on the EPYC. And then we have brand new, we have the Graviton processor, which is a processor that was developed in-house, and that is an ARM64 architecture. As of Monday, or as of last Friday, we have full support for A1 on SLES 15. So looking across the family and the families and what kind of instances are available, we have general purpose instances. These are instances that are both sort of targeted towards both compute and memory workloads that are general purpose, obviously. And then compute intensive, so where you've identified that a workload is more compute intensive, these are the instances that you're going to want to use. These are the C series, so the CC is previously CC and now C series instances. Storage optimized, those hit the H's, the I's, the D's, and then we have memory intensive instances like the R series, the R3, R4, and R5, and then the X1 or high memory instances. Those were early days. Those were a big target for and were developed with workloads for SLES for SAP. And then GPUs, our general purpose GPU, and then the GPU and FPGA compute. So we have the G series GPU for GPUs, and then we have the P series and the F series for the FPGA and GPU. Underneath those, I talked a little bit about this, but our enhanced networking is supported by the Elastic Network Adaptor. This is developed to function with the DPDK, and more of that DPDK functionality is sort of finding its way into the device itself or into communication models that customers are using. And it will provide in our N series instances up to 100 gigabits per second in a placement group. So you need to have close proximity for your instances to get the full functionality of that. We don't have too much networking here in between. These drivers are open source, so the API is fully detailed, and you can read the driver. It's available today, and that's released upstream. So our group who is working on it is constantly pushing the changes that they're making to the Linux kernel next.
So you need OpenMPI 3 for this? Because we don't have this on EC15 yet. It's still OpenMPI 3.
So, well, we need to work on that.
Okay.
Yeah.
This is good input. Thanks.
Great.
Yeah, there's a fake for the FNA driver, and I'm going to stick OpenMPI 3 into that fake.
So just to look here, up to 28 cores, delivering enhanced per core performance. The AVX 512, we have some instances that support the previous generation, right, the Broadwell with the AVX 256. But our C series and later instances are all going to the C5 and is an AVX 512, has full AVX 512 support. And there's tons of Intel tools that are available, obviously, for development. Many of those are available through the AWS Marketplace, so if you're looking for a way to have ready access to the compiler of your choice, then that's an easy way to get it for an on-demand cost. I don't have a slide for the AMD, but I'll point out that the EPYC does have does have a place in this family. But the Graviton processor, I do have a slide on, and I just want to make sure that I point this out again. Where we're going with this is you know, for targeted workloads. I'm very interested in how that can those targeted workloads can include HPC, and so I'm very interested in talking more about how this can work and what you see as a potential part of this process, and what we can work on together to ensure that we have full support. The chip itself is developed in-house, so we're not only iterating on the software that supports it, we're also iterating on the chip itself. So we'd like to know more about what your experience is. Just to talk a little bit about the types of instances that are really targeted toward these workloads, and I just want to point out that all of these are support SLES 12 and SLES 15 as well. But one of the things that I thought was really interesting here was just looking at the stack and the way that this stack is expected to sort of fall on the AWS architecture. Talked a little bit about the EDA work earlier, and this is a very important part of all of our lives, I think, which is the license manager. In many cases, you know, the license managers in previous iterations were tied very directly to the MAC address of some specific system, and nowadays they've had to decouple that because we're using more and more virtualization. But there are a number of tools that are out there being used today on SLES clusters for HPC, and those are almost, I think most all of the license managers that are not tied to a Mac device will function on AWS, but Univa has one for sure that's used fairly frequently. So auto-scaling, very important component in the way that we build out our infrastructure, and so almost all of our native plus parallel cluster tools leverage auto-scaling to ensure that they're ingesting data across the maximum number of nodes. It's very similar here, but with the C5N, which is a compute-intensive high performance networking. So The N series gives you the 100 gigabits of network bandwidth. This is across the Nitro network card. So Nitro is a functionality that we have introduced that provides you with the access to the high-speed PCI devices that are necessary for high-performance compute workloads. And then here's a review of the P3 instance. So this is one of the latest P3, P-series instance types that's available, up to a petaflop of computational performance from the 8x large, I believe. And then actually the NVLink functionality is there in the larger instance, P3 series instance types. So there is, the smaller one does not support NVLink, but once you get to the 8x large, full support for NVLink. The FPGAs, so it's up to 8 Xilinx UltraScale 60 nanometers FPGA devices, providing both the just programmable logic cells, the PLCs, as well as the DSP blocks. And obviously the A1, just want to highlight that one more time, that this is the flexibility here I think is very interesting, and I would like to see more work done with these, and I'd love to hear your feedback on your experience. Software ecosystem here, all of the things that that you would expect from the standard for standard support on AWS instances is in process with the A1. So even container-based workloads, which I know are sort of up and coming with the technology around HPC, fully supported. So any of the expected configuration requirements that you would have around creating the cluster and leveraging native products and services on AWS will be there today. Yes?
Might be a silly question, but Singularity fully supported?
I don't know. I'll have to look.
Okay.
Yeah, I'll find out for you. So just to look, turning back to SUSE Linux. SUSE is fully supported enterprise Linux on AWS today. It's been around since 2010, March 24th.
March 24, 2010 was the first image release. I had to look it up this week for some reason.
And we're collaborating intensely to bring you better HPC performance. So looking forward to increasing the amount of service integration we have here. A lot of the same tools are going to be there in the HPC module that we want, that we're using today with our customers. There's a lot of parallel involved. Like I said, Univa is there with full SLES support, and Bright Computing provides SLES support. Those are all partners of ours, and they're developing clusters for customers today. So the core of all of our instance computing is based around the Amazon machine image. The Amazon machine image is available today to customers. Are SUSE maintained? So Robert Singh is responsible for providing images and maintaining those on EC2 today. We have marketplace maintained images. Those marketplace maintained images that provide SLES today are passed through to the ones that are SUSE maintained. So you may hear people talk about marketplace images and how those are maintained by AWS. But in the case of SUSE and today and other distribution providers, the marketplace images are provided and maintained as a direct pass-through to the ones that are provided directly from the SUSE team themselves. And then we have a broad set of additional images today that customers can take advantage of to supplement whatever it is that they're doing on SUSE. And then over here, there's the idea of your machine image, but one of the things that we constantly talk about is once we have software that we know is going to be difficult to install on standard nodes, we don't want to have some sort of an installation routine that doesn't take advantage of the ability to create my own image that already has that software built in. So to decrease the amount of time, you want to use some sort of process for building your own images. Obviously, there are many tools out there in the world today to do that, caveat emptor here is that there are tools out there that can complicate the way that things, the way the structure of the pricing model works for SLES. And I have an example slide for this, so just know that in creating your own images, this is very important, and I'll get back to it. The structure of an instance pricing has two models. One is this bring your own subscription, the standard model. So if you're leveraging your own subscriptions today for your instances, those instances are created with a billing construct that includes the infrastructure costs and then any reserved instance discounts. So reserved instances are a way of purchasing your time on the instance up front at a deeper discount. Those reserved, since this is a billing construct, it's attached at the time that an instance is started. So if you have more reserved instances than you have instances running, as soon as you start up another instance, one of those reserved instances from the pool will be applied so that the discount is applied to the running time for that specific instance. But your subscription cost is separated. In the case of an on-demand instance, the subscription cost is included. So with an on-demand instance, we've attached, or Robert's team has assigned what we call a second-party billing code to the instance itself, or to the machine image itself. And the machine image has created an instance with that billing construct in place. Tools like Packer separate the snapshot from the Amazon machine image, the snapshot that backs that Amazon machine image, and then re-registers it as a machine instance. And that can have the effect of losing this subscription association. And so you end up with something that looks more like this when you expected to have something that was price included. So while the cost structure changes accordingly, it may be something that you want to avoid. So be careful of the way that your images are built and how you create those. And this would be a great place, and this is a great place, I think, to plug the SUSE Insulatus tools for handling your image import and image management. So one of the other things that I think is very interesting for customers who are doing grid work or doing work where you want to span multiple virtual private networks. So the AWS or EC2 has a networking construct called the virtual private cloud. The virtual private cloud gives you a non-routable IP address space to which you can attach connections. But those connections don't necessarily have to be in the context of an external network communication. So we can, through the software-defined networking infrastructure internal to AWS, ensure that there is a direct communication from one VPC to the next. So you can take advantage of both transit gateways on the local configuration, And then you can use private link to have access, direct access to services that you wouldn't normally have had access to if you had only allowed for non-routable communications. So that's like S3 or RDS or some communication that is necessary as a service endpoint for your systems. You can do that via proxy through a network load balancer. And you can see there's a lot of customers who are doing this today, and it can be very beneficial if you want to create a larger scale network than you have access to in a single VPC. So, target models for running HPC software on AWS. Obviously, we all know the self-managed version over here. But then there's also hybrid models. A lot of customers do burstable models. So we have a lot of customers who like to burst to the cloud, or to have some sort of an intercommunication where they're creating a dev and test environment and leveraging that back and forth. But then there are other options that we'd like to see more of. The great options for helping customers to get introduced to your stack can be providing a full service model. There's also something we call the quick starts, which we developed one for CAP. David Roach's team and the CAP team worked together to build out something that we just announced this week. Those allow customers to have sort of a fully supported configuration with a one-click deploy to test and to review as a reference architecture. So now we're going to talk a little bit more about Spot Fleet. Obviously, this slide has a big spot there for me. The idea here is that we're increasing the amount of workload that we can handle at any given time, but we're not creating a commensurate cost, right? We're creating an efficiency in our cost model, and we're leveraging the opportunistic times for lower compute costs to get where we want to get in terms of our total compute time. A key component in ensuring that we're getting what we want is finding ways to notify the cluster that we have an increase in the number of nodes that are available. So if we have a configuration where we can do that, we'll leverage some of the native tools or even some other queuing models for actually identifying that auto-scaling has occurred and we have more nodes than we had before, or we have fewer jobs that we have fewer jobs and require fewer nodes, and so we're scaling back, so we want to decrease the number. Yes?
A point that was brought up in a session earlier I thought was quite clever is they use the Slurm scheduler power on, power off feature.
Yes.
And they would use the start and stop script functionalities of actually powering on and powering off nodes to actually invoke and then of course tear down nodes.
Precisely.
With the cloud structure, which is kind of cool.
Right, and so what they can do that from the context of what we call an auto-scaling lifecycle hook, and the lifecycle hook can execute the command as a result of the event. So if it's a scale-up event, they can power on, and if it's a scale-down event, they can power off.
Yeah, so the cluster is always aware of the enumeration of nodes, and if a cloud-based node is idle for a certain period of time, it runs the stop script and tears it down. If it needs more nodes, it runs the start script and invokes them.
It eliminates the requirement to have a control plane for doing something like that outside of your standard network.
Exactly.
Yeah. So the other component here is to use what we call a launch template. A launch template is a way to combine your efforts around what kind of scaled out requirements you have. So you may have a very small amount of fleet that you decide is absolutely required, and because of that it's going to run at it's going to run as an always-on instance, right? And identified as through reserved instances. And then you'll have a spot fleet that will increase and decrease as the frequency requirements go. Those can be defined in the context of a template. So I can say in this template, I want to make sure that I have this many nodes, and of those nodes, this many can expand or contract based on the workload and based on my scaling requirements, but then also in that context to define a price, a maximum price that I'm going to pay. So that looks a little bit more like this, where I have reserved instances. You see that I can have sort of 3 different kinds of models where I'm leveraging this. I can have more reserved instances, fewer reserved instances, and even fewer reserved instances. The on-demand instances themselves those are the things that I can leverage, but they're going to still be the same price as a standard instance. Unlike the reserved instance, they don't have any kind of applied discount, right? But then the spot gives me a way to have a variable price. So as the price increases, I'll find a place where I may have a requirement to have more nodes that at a peak time I can leverage the on-demand when that happens. But for the most part, as that the demand drops off for other people, I can still continue to take opportunistic access to the spot fleet. I'm wrapping it up. So things we're working on is delivering the HPC module through the AWS marketplace. We're looking forward to making that available to customers in an on-demand way. The other thing we're looking forward to is parallel cluster support. So we have a utility that we use for provisioning a cluster, and that is pretty easy to do. It requires just a simple configuration file. The size of the cluster itself can be variable based on the demand and workload, and then you can choose from a number of schedulers that are fully supported, including Slurm. And the configuration itself is highly malleable. This slide I put in here because there's something that I wanted to point out, is that one of the things that the parallel cluster has been developed around is using the simple queuing model to ensure that if you have some sort of a job that can take advantage of the queue process, you can scale up the number of nodes based on the number based on the amount of work that needs to be done, if that's in some way discrete, and you can feed that through the queue service. You can then provide the back-end nodes through a simple process, through that just by measuring the queue depth. And then also coming soon is full support for the enhanced the elastic fabric adapter. This will support the libfabrics API, and also will support standard RDMA communications. So once the EFA is available, the RDMA communications become much easier. And this is developed through a very similar process and related to the EMA. Something that our Nitro system makes available. But that'll be available on the C5N, the 9XL, the 18XL, and then our P3. The D means that there's a direct attached storage. There's direct attached storage devices that are NVMe, and the N is the 100 gigabit networking, which is required. With that, I'll take questions. Yes.
For workloads that have a high node density, where do you observe contention?
So obviously that's gonna be job dependent, right? So.
Yeah, I mean, I'm just wondering, I mean, by observation, where do you see contention? And of course, you would want to design around that. So
Yeah,
that's
so, and we do spend we have a group of scientists who spend most of their time ensuring that they can tune workloads to the optimum ability across those instances, whether that's increasing the instances, changing things about the way the memory pressure is handled, or changing the way the ingestion works. They're fully dedicated to doing that. And so we have customers who are looking at workloads and concerned about whether or not they're tuning them to the right levels. We can bring those scientists in to help them create the optimistic view of that workload.
So,
yeah.
so it would behoove you to come to the table with a specific workload use case in mind, or workload use cases.
Definitely, yeah, definitely. So the question being, does it behoove you to come to the table with a specific workload? Yes.
AWS at SUSE.com.
Yeah.
Just a general percentage, how much do you see the better supplied, AWS supplied versus private supplied images? How many people are coming in with their own versus using what you guys have available already?
Well, so the image that we provide is fully customizable. We expect people to come to the table and identify that as a place to start, right?
Yeah, just as an example, we're doing exactly that. We're taking the SUSE image and then pointing it at a copy of our repos so that we can make machines that mimic what we have in-house for our engineers. So
Excellent.
we're using their image, but not totally. You know, their image and then adding on to it.
Yeah.
You're booting from their image.
Yeah. Pretty much. Yeah. It's a bootstrap. Yeah.
Yeah, once you get that image up, then bringing it to the table, that's no problem. We also have so there's the EC2 image utils that Robert Steen maintains from SUSE, and if you have an image that you have created on premises and you want to move that onto AWS, you can move that onto AWS as either a bring your own subscription or an on-demand instance through those tools.
So I would have a question for you, but also for everybody else here in the room, at least to the people who are using the HPC module. Is there anything what we can do to make things for you, for your customers, for everybody else using it, easier, better?
Well, so I would say you're in the process of doing it. This is on the backs of giants, right? So many people have been involved in ensuring from top to bottom that we have the resources that we need to move forward fast for SUSE customers who want to do HPC on AWS. And those, as customers find themselves in, needing more assistance or wanting different things, facing challenges, we want to make sure that they're coming to us and coming to SUSE to resolve those issues. And Eamon, you said AWS at SUSE.com. So if a customer is does have a request, a specific request, and they want to know more, or they want to engage us for more assistance, then we'd be happy to have them.
Do you see requests regarding HPC? So I think at the moment we're starting to hear a little bit more about it, especially with some of the upcoming work that Amazon is doing around like the EFA adapter and opening up to different types of workloads. I mean, I think we're just putting it, AWS and SUSE.com is out there as like, we want to engage more, to start seeing what people are looking at and what they're doing.
We want to make sure that they're able to bring their workload as simply as possible to AWS using the tools that they know from their SUSE experience.
And I think there was one session earlier today from a partner that's starting to do more security.
Yes.
They're offering like an HPC as a service. I don't know the details of it, but they're a SUSE solution partner, probably engaging us feedback.
And there's just a tremendous amount of overlap in the partners that we have in the space, the ISVs that we're working with generally. So it would be great to unify that for customers who are working on today.
I mean, once we have FNA and OpenMPI3 and RDMA capabilities, that's going to open up a whole set of workloads that are not available today, right? So,
Can you put me on this feature request for OpenMPI 3? Just so that I...
yeah, Jay should be on there already, so I'll add you to it.
I don't remember seeing it, but
Yeah.
just make sure.
Yeah. Okay, thank you.